Alright, so today we're going to go over pressure and sound waves. We'll talk about the properties of these waves, especially including, actually I'm going to probably write here, pressure and sound waves. I also maybe mention that we'll look at wavelength, frequency, and speed of a wave. And we'll also briefly discuss transverse and longitudinal waves, which is something we've been over briefly, but we'll cap again. And actually, we will not have these things on here at the moment. We'll leave that for a later time. Okay, so let's see here. I'm going to go over first the slides that are going to be marked as, it starts as a V equals LF, and then actually, I'll rename that a little bit. It'll just be talk about pressure and sound waves, and then I'm going to go over these slides here, which is called 3 waves, and so you can find those slides online. So here's our cartoon picture of what a sound wave is. It looks like, and we have a nice visualization here. I guess let's see if we can open that briefly here. I'm going to move this over. Okay. Good. So here's our traveling wave here. It's a reminder of a transverse versus a longitudinal wave. Just as a reminder, the displacement for a transverse wave is, let's see that again, the displacement is only in the perpendicular direction to the motion, whereas the longitudinal wave, if you were to tie a little string on this, then you would see that the string only moves back and forth, and the wave is also moving back and forth. So this is a difference between a transverse and a longitudinal wave. And sound, which one is that one more like, a transverse wave or a longitudinal wave? Well, it's more like a longitudinal wave because the particles of air are actually moving backward and forward, and you can remind yourself of that if you look up the PHET, the PhET simulation, regarding sound waves. So, okay, so we'll go back to the slides here. The point is that we have alternating places of compression. For example, that would be this. In this case, the dark areas are considered as the compression. The light areas in this cartoon are considered as the rarefactions. This just means the place where the particles are most spread out, but they're not crunched together. And we see that that crunchedness, very similar to the analogy of that slinky, that moves over the space as time marches forward. So this is the propagation of a sound wave. And so it says pressure in here, and we'll talk in a moment about how to quantify pressure and what that means. But here's a nice little animation that I like that sort of shows us a visualization of these air molecules. So this is sort of an idealized version. In contrast to the simulation that we tried, it's not like there's not all that random motion also involved. It's just simply particles moving left and right. And you'll notice that there's 2 or 3 red dots here that are shown. The red dots are no different than any other dot. They're just a couple of them that are highlighted to show you what's really happening. Is that if you just look at any one of them, let's look at the one in the center here, we notice that all that's happening is it's just moving back and forth, right? That it's not actually moving across the whole screen. It's actually just moving left, right, left, right. But yet we see that there's this aggregate that is actually moving. So not any one particle is like surfing with this wave. It's just that the compression itself is moving. So this is the propagation of the wave. So again, you can see that the places of compression and rarefaction are moving, whereas the particles themselves are just simply going back and forth, longitudinal wave. Can you identify here the wavelength of this picture? We have a tuning fork which creates sound waves, and then I guess we have sort of a channel, and then the sound waves are propagating through the channel. Where are the places of high pressure? Where are the places of low pressure? Well, if I were to look at this, I would say from here, this place of high pressure, to the next place of high pressure would be the length of my wave. In other words, the distance, if this was a snapshot in time, this is the distance that you'd have to go before this pattern repeats itself. So from here to here, I would say would be the length of the wave, or the wavelength. Where these are areas of high pressure here, where it's crowded, and where it's the least crowded, you could say that it's an area of low pressure. So let's talk about pressure. What does that actually mean? So particles are moving around in a container or in a room, and they can bounce off the walls. And every bounce creates a force on the wall, very much like if you were to throw a football at your friend really, really hard. When they caught it, they would feel some force. They would feel some pushback. So imagine that there's billions of these little molecules, each one of them by themselves not particularly massive, but together, bouncing off of a wall, they actually exert a force, or they push on the wall. And so each collision gives some force on the wall, and the net force of all of those collisions causes the gas to have a pressure. So collisions with the wall create, for example, of a bike tire here, create a force that's perpendicular to the tire wall. So if, for example, I took this area here and I made the area twice as large, that little patch there, then there'd be twice as many particles that it would hit at every second. So does that mean the force is doubled? Yeah, it does, because we have more area. But does the pressure double? No, maybe not. It does not. So the way that we say this then is that the pressure is the force per area. And this is something that we've already sort of worked through before in our previous exercises, just looking at the units alone, but now we'll go into a little bit more detail. The pressure is defined, for example, 1 Pascal is what is called 1 Newton per square meter. And a Newton is a unit of force, and square meters, as you might guess, is a unit of area. So just to give you an idea, the pressure from the atmosphere, if we're at sea level, which in California it's close enough, at least near the coast, we call it as 1 atmosphere, or 1 ATM, and this is about 100,000 Pascal, or you could think of it as 10 to the 5th Pascal. In the US, we of course like to use some weird different units. Maybe you've heard them before. Pressure is expressed in pounds per square inch. This literally means if I have a spot the size of a quarter or so, that there's the equivalent of 15 pounds of weight sitting on it. It's pretty crazy, right? So you might ask yourself the question, well, why is it then that I'm not completely crushed? Because I'm a lot more than 1 square inch. I'm many square inches, right? And the answer is, as we'll see, is that it's actually that your body has evolved to be able to push back with that much. So we'll take a look at that in a second. So 14 or 15 pounds per square inch is the same as 1 atmosphere, which is the same as 10 to the 5 pascals. And in your textbook, they actually just say 10 to the 5 pascals. So this is in chapter 3. It is discussed about, and I'll bring it up on the video when the time comes. So, okay, so which of these has the highest pressure, a stiletto shoe or an elephant? Well, it really depends on how much that thing weighs. So, for example, I can work out an example for you. So, I will bring up the video here, and here's the so looking at like a stiletto heel versus an elephant, we could ask, well, what is the pressure for these two situations? So I'll write stiletto, even though I don't even know if I can spell that correctly. I think it is there. And then there's elephant here. I'm just going to make up some numbers here. So, for example, I know that a person weighs about maybe 80 kilograms, which in the unit of force is going to be equal to about 800 newtons. We're going to actually multiply that by 10. That gets us to newtons. The elephant is going to be about 1 ton or 1,000 kilograms, and so that's going to be 10,000 newtons will be the force. So here's the deal. We'll say that the stiletto, let's just imagine that this person is just standing on one heel of the stiletto, right? So here's my kind of person here, and then, okay, just maybe, I don't know how to draw this person, but they're standing on one foot like this, and here is their little heel thing, and they're just standing on the heel part of their, okay, was never maybe born to be an artist, but there we go. There's the person standing on the heel, there we go, like one little spiky shoe. And we can say that the area right here that comes into contact here is going to be 1 square centimeter, let's say, right? So let's do that here. So 1 centimeter squared So again, we've wanted to put that into meters squared, so I'm going to say this is 1 square centimeter here. That is going to be, I know that there's 1 meter is the same thing as 100 centimeters. If I square here, that's going to be 1 centimeter squared times 1 meter squared divided by 100 squared, which is 100 times 100, or 10 to the 4 centimeters squared. So in other words, a centimeter squared cancels out, and I'm left with 1 meters squared divided by 10 to the 4. So in other words, I have 10 to the minus 4 meters squared is my area. So I'll say my area is this, right? So in other words, going by this idea that pressure is going to be force per area, I can say that this is 800 divided by 10 to the minus 4. There's square meters, there's newtons. Now, we've been trained to know that newtons per square meters is a Pascal. So remember that Pascal is newtons per square meter. That's one of the ideas here. Or in other words, pressure is force per area. Those are both the same idea there, right? So the P here in this case means pressure, and the pascals is the unit of pressure. So I can do this math here without using a calculator. I can say that that's 800 times 10 to the 4. Remember, because we take 1 over 10 to the minus 4, that just becomes 10 to the 4, and this is in pascals. So we can do times 10 to the 4, so 800, and then do 1, 2, 3, 4. So fill this all in with zeros. And this is going to be, that's 3 zeros, so it's 8 million, or 8 times 10 to the 6 pascals, or 8e6 pascals. That's what we've got, 86 pascals. Now let's do a little estimate for the elephant, okay? So here's the elephant that has 10,000 newtons, right? Quite a bit heavier than the person in our estimate. But we've got to figure out the area of the hoof. So the hoof here, I don't know, how big is this kind of hoof here? Well, I don't know, I'm going to estimate it as like maybe, let's come up with some easy number here. So like if it's a 10 centimeters by 10 centimeters, something like that, it's like, it's about this big. Yeah, it seems okay. Let's just do that. So let's say it's 10 square centimeters. And I found out from before that if I want to go from square centimeters to square meters, it looks like I just divide by 10 to the 4. That's what we figured out over here. So 10 square centimeters, I could also do this multiplying trick here, but if we just divide this by 10 to the 4, so divide by 10 to the 4, then I'm going to get that that's 10 to the, what is this? That's 10 divided by 10 times 10 times 10 times 10. So you can see that this is 1 over 10 to the 3. So I can also do this by 10 to the 1 over 10 to the 4. That's 10 to the 1 minus 4, or it's 10 to the minus 3, yeah? Okay, so we have 10 to the minus 3 is our area, square meters. So, let's see here. So the pressure then is going to be force per area, and we'll have 10 to the 5 newtons divided by 10 to the minus 3 square meters. So that's 10 to the 8th pascals. How did I get that? Because I did 10 to the 5 divided by 10 to the minus 3. So just as an example here, it's 10 to the 5 minus a minus 3, which is plus, and that becomes 10 to the 8th. So in other words, this is my pressure here for the elephant, this is my pressure for the person. Now I want you to also notice something, is that, let's say I got this wrong, and it's actually like, I don't know, maybe the surface area for the elephant is like, maybe I got it off by a factor of 10, then it might be 10 to the 7 or so. So then if we had a little bit of a larger area here, I think what I'm trying to get you to realize is that 10 to the 6, this is 8 times 10 to the 6, so 10 to the 7th versus 10 to the 8th, that's only a factor of 10 difference, but an elephant is obviously much, much more heavier than a human, right? But the point that I want to impress upon you is that these numbers are pretty similar, actually. They're within a factor of 10 of each other, which means that, for example, if you brought an elephant out onto some ice, and you brought a person with stiletto shoes onto some ice, they might both have a good chance of breaking through the ice. And it doesn't necessarily have to do with how heavy it is necessarily. It has to do with the pressure, how well we're going to pierce through something. So anyway, so that's kind of like a little example that helps you maybe to see the connection and see how pressure is working there. So there's the stiletto versus the elephant. If you didn't follow all that math, the most important thing I want you to take into account here is this idea of how do you calculate pressure? It's force divided by area. So just like it says here in the slide here, force divided by area. Okay, so moving on, why, if I mentioned that 15 pounds per square inch and we added up all the surface area of our body, we'd find that there's about 40,000 pounds pushing on us from all directions. And so, why doesn't this crush us? It's because our body is also able to push back with that much force. And so that's kind of amazing. Thank you, body, for protecting us from the crushing of the atmosphere. If it were crushing us, we wouldn't be here. Okay. Just as to test your understanding, I know this one already has the answer, is that if a mass is sitting on top of a piston and it's pushing down on this thing, hopefully you can see that the pressure inside of this cylinder is going to be greater than the pressure of the atmosphere outside the cylinder because you got this big old mass sitting on top of it. So if you're getting that and it's making sense, it's going to be a higher pressure, then I think you understand what you need to know about air pressure for this course on sound and music. So here's the picture that you'll see on page 27 of the textbook. The deal with this sound and pressure is that sound is a fluctuation in the atmospheric pressure. That's the connection here. But the really interesting part about it is that the pressure is just fluctuating by a very small percent. It's only 1 part in 10 to the 5. That's much less than 1% fluctuation, right? That's like 0.01% fluctuation, I think. And that's kind of interesting. Your ear is a very sensitive detector. It can notice if there's pressure changes that are on this order. It's not like it's actually going down to 0 pressure, right? It's pretty much the pressure of the atmosphere is staying at whatever this 10 to the 5 or 100,000 newtons per square meter are, but it's just fluctuating by a very small amount. It's getting slightly more crowded with molecules, slightly less crowded, etc. Okay. So by the way, if 1 atmosphere is 10 to the 5 pascals, how much is 0.8 atmospheres? Well, you can do this by just dividing or just say multiplying by 0.8, and you'll get that it's 80,000 pascals. So Richard Feynman was a kind of a funny guy, scientist, that said, once you see one wave, you've seen them all. And so the concept that we want to extend is that we study waves in this class, and we study them in a variety of different ways, and I show them in different patterns and configurations so that you can get a sense for thinking about how to describe these waves. So one of the activities that we do in this class is to actually take a rope and to give it a flick up and down, and we'll see that there's a wave that travels along the rope, and this is kind of transverse wave, but this one is a nice one for visualization because it helps us to visualize the propagation of a wave. As you know, the transverse wave is different than a longitudinal wave in the sense that sound, as a longitudinal wave, basically has particles moving back and forth in the same direction as wave propagation, whereas this example of the string has the particles on the rope, or just the pieces of the rope, are moving up down, whereas the wave is moving from left to right. So just as a reminder, the transverse wave is where the motion of the medium is perpendicular to the direction of the wave propagation, whereas a longitudinal wave is where the motion of the medium is in the direction of the wave propagation. So anyway, so that's kind of the language here is the medium is, we're talking about the material in which the wave propagates. And so, like, for example, that could be water, or it could be some air, or it could be the rope. And up and down, for example, we might mean as if the wave is traveling from left to right, then it's traveling up and down means perpendicular to the direction of propagation. Back and forth means in the direction of the propagation of the wave. Okay, so here's an important formula here that we are going to use over and over and over again. So you got to know this one. This is super important. Stop and write it down on your crib sheet. And by the way, yes, you're allowed a crib sheet for all the exams, including the final. A page front and back with anything you want to handwritten on there. And the formula that we're going to work with here is that frequency is the speed divided by the wavelength. Okay, so the concept here is that we're trying to think about the amount of time that it takes for this wave to get to the next location. Okay, so for right now, you can just take this as a formula, and then we'll actually dissect it in a bit and try to figure out where it actually comes from. The idea here is that the length of a wave is the distance between one peak to the next peak. Okay, it's going to be this Greek symbol lambda. By the way, we'll use that because L is sometimes often taken for talking about a distance from one place to another. So we're using the Greek letter for L, which is length, right? So that's why we use lambda. So if you were to shake a rope up and down, you'd find that there's an oscillatory pattern. And if you took a snapshot of this, you'd find that the distance from one peak to the next peak, or from one trough to the next trough, would be the length of the wave. And the way that the frequency would be the number of times per second that you're wiggling this rope up and down. So what am I going to say here? So they're related like this. The frequency is the velocity divided by the wavelength, or the speed divided by the wavelength. And by the way, the range of human hearing is in frequency from 20 hertz all the way up to 20 kilohertz, or 20,000 hertz. So if we were to convert this into a wavelength, we can actually see what kinds of wavelengths these are. Let's practice and see if we can figure out what some of these wavelengths are. So I mentioned that the lowest sound that we can hear is a frequency of 20 hertz. What is the wavelength here? Well, if we go back to our formula here, we see that, I'm going to write this down here, frequency is equal to V over lambda. I'll write that down here. And by the way, there's a triangle that we can actually write with respect to this. We can actually say V and F and lambda. And this is kind of a mnemonic device that you might consider writing down in your crib sheet. This tells us that for this equation here, we can say that V is equal to F times lambda, or lambda is equal to V over F. And yeah, and that's all the different varieties here. So the way you can use this triangle here is basically V is equal to F times lambda, because they're next to each other. F is equal to V over lambda, just like this one, because V is on top of the lambda. If you wanted lambda, that's V over F, and you can see that one over here. So those are the kind of the three incarnations. It's all the same equation, but sometimes it's just nice to have a little mnemonic to help you. So you can draw yourself a little triangle, something like this, and that helps you to remember. So anyway, so we have an F. Let's just say that the speed of sound is 344 meters per second. That'll be our kind of common number. This is the room temperature number of the speed of sound. Now remember that that does change if the temperature changes, but if you're not told a temperature, remember that for every degree, it's only about 0.6 meters per second faster. So even if it's a hot day, it's only going to be off by a few percent, right? So this is kind of a good estimating value here. So if we want to figure out lambda, the length of the wave, then that's going to be V divided by F. And so you can see here that that's 344 meters per second divided by 20. And then like, uh-oh, well, it hurts. How does that? Oh, yeah, that's a 1 over second. So the 1 over seconds and 1 over seconds cancels out, and we're left with 344 divided by 20. And that's going to be, if I use my calculator here, let's just, I'll bring up calculator. I'll do 344 divided by 20. It's 17.2. Good. So here's 17.2, and my unit is meters, as you can see here. My unit's meters is the only one that stays. So that's a pretty long length of a wave. So in other words, like if we went back to that idea where we had the places where the particles were more condensed and less condensed, and then more, more condensed, something like this. You remember this picture here from earlier, and there's a little bit less atoms here, less atoms here. The length of the wave here, right, lambda, would be, in this case, 17.2 meters, right? That's a lot. That's actually like 45 feet. So the distance from one high density region of particles to the next would be 17 meters. Okay, so that's for the very low frequency sounds. So low frequency, long wavelength it looks like. Next example, let's take the frequency of 20 kilohertz. So 20 times 10 to the third hertz, or in other words, 2 times 10 to the 4 hertz. If we take that example, we can see that we want to figure out the lambda is going to be 344 meters per second divided by the frequency, which is 2 times 10 to the 4 per second. So in other words, we're going to figure out this wavelength again. I'm going to go back to our calculator, and I'm going to literally just do pretty much the same thing, except for there's going to be 20 E3. So I end up getting 0.0172 meters. This by itself is acceptable, but do you know how many centimeters that is? It's 1.72 centimeters. And you can use this conversion trick, for example, multiplying by the fact that there's 100 centimeters in 1 meter, and you'll slide that decimal place over 2, and you'll get 1.72 centimeters. So let's go back to our slides here and see if everything's cool. Looks like that's right. 20,000 hertz is 1.72 centimeters, whereas the 20 hertz is 17.2 meters. By the way, I also wrote down here that a lambda equals 1 meter gives a frequency of 344 hertz. Can you figure that out on your own? Please try to pause for a moment and see if you can plug into our formula that we just discussed, that V equals F times lambda, to figure out what is the frequency if I gave you that the wavelength was 1 meter and that the speed is 344 meters per second. Okay. So continuing on, just for review here, that pressure is force divided by area. The pressure has units of pascals or newtons per square meter. The background air pressure, while it is a little bit different from 100,000 newtons per square meter, in most cases we'll just use 100,000 newtons per square meter. And so 10 to the 5 pascals or 10 to the 5 newtons per square meter, that's going to be the unit that we use for, that's going to be the value that we use for our pressure and the different problems that we experience. And then the other thing that I wanted to hopefully that you got here is that the pressure wave fluctuations are very small. They're about 10 to the minus 6 atmospheres. That's a part per million, or 0.1 pascals. So 1 part per million fluctuation is what your ear can detect. Okay, so anyway, here's this little triangle here that I mentioned. You can see here that V is equal to F times lambda, so the F and the lambda are next to each other. F is equal to V over lambda because the V is on top of the lambda, and lambda is V over F because the one is on top of the other. Let's try some practice. So this is where we really develop our skills here. Suppose a mandolin plays an A, which is 440 hertz. What is the wavelength of this sound wave? Okay, give you a pause for a moment and let you calculate this. You can see if you can guess it for now, or you can actually just try simply calculating it out to see if things can make sense. So I'll pause here and be back in just a second. Okay, we're back. And what did you find out? Well, hopefully you found out that it was less than 1 meter. And let's explore why this is. So if I take a look at the 440 hertz, F is 440 hertz, or inverse seconds, and the speed didn't say what the speed was, but I wanted you to think about, well, it's probably somewhere close to 344. Now this was a logical step that I wanted you to think about, was that, you know what, even if it's a little bit warmer of a day or a little bit cooler of a day, it's not really going to change by that much, actually. It's just going to change by a few meters per second up or down, depending on whether it's a hot or cold day, respectively. So we can use that triangle here. So I'll just remind you, this is the triangle here. We were given an f, and we figured out a v because we guessed it, and we need a lambda. So lambda is v over f. That's our equation that we're going to use. Lambda is equal to v over f. When we use that here, we'll see that it's 344 meters per second. And we're going to divide by 440. Hopefully you're starting to feel like, oh, this is doable. I think if I practice this enough, I can get this. We have 344 divided by 440, and already you can see that that's going to be less than 1 meters per second. If I go back to my calculator here, I'm just going to type in 344 divided by 440, and I get 0.78. So this unit is in meters, as you can see, and we have 0.78 meters is our final answer. So if you're getting comfortable with this, that's the goal. Even if it feels like a little bit repetitive, we're going to repeat this a few times because I really think this is an important skill to develop here. So the length of the wave for that particular note, an A would be the middle A on a piano, is going to be 0.78 meters. All right, let's try another example. A piano string is tuned to a frequency of 688 hertz. What is the wavelength of a wave that propagates along the piano string? So this is kind of a trick question. So I would say don't even worry about pausing right here, because if you think about like what's being asked, we don't know anything yet about speed of waves on strings, actually. We do know about the speed of a sound wave through air, but the speed of a wave on a string, well, maybe that's different. In fact, one of the things that we noticed is that the waves on strings are actually transverse waves. And so we haven't actually discussed this yet. And so therefore, there's not sufficient information to determine. Okay, so this kind of trick question is just meant to highlight that the speed of a wave on a string could be different than the speed of a wave in air once it's created that sound. Now, I could have asked a different question. Well, what would be the speed of, the wavelength of the sound in air? And we could do that by exactly the same calculation we just did before, and we would find a slightly shorter wavelength than we did with the 440 hertz. But we're not going to do that just now. Okay, so I just wanted to highlight that the point of this question is to get you to realize that the speed of a wave along a string is not the same as the speed of a sound wave through air. In fact, that they're different, and we will handle those two cases separately. What type of sound would travel faster through air? Do you think it would be a high-pitched sound, a low-pitched sound, or that they're all at the same speed? Go ahead and pause and maybe just confirm with your friend who you're watching this video with. What do you think it is? This is a good review question. So, if you remember from before, all the frequencies travel at the same speed. And so this is kind of one thing that be helpful to remember as you're solving problems, is that you don't need to consider the frequency of the wave when you think about the speed, that they're all traveling more or less at 344 meters per second. And I say more or less because if it was a different temperature, then you could say that it travels at, if it's a hotter temperature, it could be a faster speed, etc. Okay, this is a repeat slide here. Knowing that the water level goes up and down as a water wave passes by, how would you categorize that wave? So I'm thinking about, you're at a lake, you see a little rubber ducky sitting on the lake, and there's some water wave that's passing by, and the little rubber ducky's going up and down, telling you that the water level is also going up and down. How would you categorize this wave? Well, I would say it'd be a transverse wave. And the reason is because the rubber ducky is moving up and down, whereas the wave is moving from left to right. So a sound wave, again, what is this an example of? A conservative wave, a transverse wave, longitudinal wave, or a string wave? So hopefully you know by now that a sound wave is a longitudinal wave, but most importantly the reason is because the molecules themselves are moving, let's say, from left to right, and also the sound wave is moving from left to right. And that's what makes it as a longitudinal wave. Okay, so let's examine some musical range in terms of wavelength. So here's something interesting. There's these different Cs, the note C on a piano, and for every extra octave that we go up, we're going to go up by a factor of 2 in frequency. So C2 is 65 hertz, C4 is 262 hertz, and a C7 is about 2,100 or so hertz. So these frequencies are approximate. What wavelength of sound waves do these notes correspond to? So I want you to pause for a moment and see if you can calculate these wavelengths given the frequencies. So we're given 3 different frequencies. Okay, so we're back, and I will show you my own way of thinking about this here. We're going to again use the same formula as before, that wavelength is going to be equal to speed divided by frequency. And the frequencies that we're given here, go back over to here, are 65 hertz, 262 hertz, and 2093 hertz. So literally, we just need to plug in 344 divided by, say, 65 or 262, etc. And so we're going to do, again, meters per second, and 1 over seconds. We see that 1 over seconds cancels out, and we're left with meters, which is what we need. And again, getting back to my calculator here, I'm going to just divide this by 65. And so I'll write down the answers as we go here, and then we'll go back to this. So 5.3 meters for the 65 hertz. When I type in 262, we get 1.3 meters for the 262. And finally, I'm going to type in the really high-pitched one, which is 2093, and I get 0.16 meters, or 16 centimeters, for the 2093 hertz. So going back to my camera, you can see here that the higher the frequency, the shorter the wavelength. Okay, so that's going to be a kind of a theme that we're going to see multiple times here, and that high frequencies mean shorter wavelength. And so if that's true, I can look back to these examples here, and hopefully you chose that the answer is D. That you get about 5 meters, about 1 meter, and about 0.2 meters, and 0.2 meters would be for the highest frequency. So the higher the frequency, the shorter the shorter the wavelength. Okay, so continuing on, this is going to be our last question for this part, and then we'll move on to the next set of slides. Suppose that there is a tall and wide brick wall at a distance, and you clap, and you hear an echo of the same clap with the delay of 2 seconds. How far away are you from the wall? This might sound like kind of a funny question, but actually this is one of the ways that people do ranging, is by sending ultrasonic waves, even things that people can't hear, and they measure the time that it takes for the sound to get back, and then based on that they can figure out how far away something is. And it turns out it's actually a pretty accurate technique. And so, okay, so I've sort of drawn you a picture here, but I want you to pause and draw yourself your own picture. See if you can make some sense of this, because you have to think about this one. We can't just simply blindly apply a formula. So I want you to stop, think about it, think about what is it that you know, or you think that maybe at least you have a pretty good concept of. For example, do you know what the speed of sound is? And then see if you can figure out how far away is this wall. It took 2 seconds for the sound to go there and back. Pause now. Okay, we're back, and the sound travels from the person, they clap, and then the sound travels to the wall, and then it comes back. Well, hopefully you saw that if it takes 2 seconds to do that, then the wall is 344 meters away, which is more than 3 football fields. Okay, let's figure out how we can do this kind of problem. So here's my person. I recommend always drawing a problem when you're trying to solve these problems. You're going to find that it makes your life a lot easier. And the distance between the wall and the person, D, well, we don't know. That's what we want to figure out. There's a sound, I could draw it as a star, and it kind of sends out, and then it comes back. And it looks like the total distance traveled is actually 2D. Oh, okay. So it goes d there and d back. So in other words, I know that there's that equation distance is equal to speed times time. And I can figure out that the speed must be somewhere around 344 meters per second. The time is 2 seconds. But the distance is actually going to be, in this case, is going to be 2 times d. That is going to be the distance that's traveled in this particular case, because it's a there and back situation. So I can plug it all in now. 2d is equal to v times t, or d, the distance to the wall, is v times t over 2. That over 2 part is really important here, because it's helping us to realize that actually there's more going on than just going from one place to another. It's actually sound reflecting off of a barrier and then coming back. So that's why it's 2d, and there's our factor of 2. Plugging in the numbers, we have 344 meters per second times 2 seconds. Seconds cancel out. Divide by 2. Oh, look at that. The 2's cancel out. We're left with 344 meters is the actual distance that we are away. So that is how we solve that kind of problem. And that is definitely a kind of problem that I'd like you to be able to solve. Even if I gave you some situation like that where I gave you the distance that it is and I wanted to know how far away, gave you the distance and I wanted to know how long it would take for the sound to go there and back. Okay, good. So that is the end of that set of slides, and I'm going to move on to, these are some kind of canned slides here that I think are good and will help us to get some more review. So some of these things will be repeat, and other things are going to be helpful for you as you're working through the homework. So let's see here. I might just mention a couple things about homework since I'm kind of thinking along those lines right now. One of them is that about octaves. Let's see. I think I should probably mention that. I'm going to go back to this thing here. We were mentioning octaves in one of the slides, but I will just mention right now that an octave is going to be multiplying by a factor of 2. So for example, if you had an A that was equal to 440 hertz, then if you want to go to the next A on the piano, in fact, what I'm going to do here is on the fly, I'll just pause. Okay, well, perhaps I can't also play sound at the same time for some reason. What I wanted to show you here was that if you had the piano, for example, this is the C, and then this would be another C, but up an octave. And so we will have a chance to play with this if you go to Chrome Music Lab. Then you can already get a preview of these things. I will give you some more instruction around that in the future, but for now, that's okay, good enough. If you had an A that was 440, the next A up on the piano that would be would be an octave higher would be frequency multiplied by 2. So I think this would be A4 and this would be A5. So in other words, what I want to say is that an octave means multiply an octave up, let's say, means multiply the frequency by 2. So for example, so we did one example going from 440 to 880 is up 1 octave is the way that we say that. If we go up another octave, you might think, oh, well, do you just add 440 to that? It turns out, no, you're going to multiply this frequency by a factor of 2. So, for example, let me do something mathematically simpler. So, for example, if I had a frequency that was 200 hertz, then if I go up 1 octave, that gets me to 400 hertz, right? So this would be F1, F2. If I go to F3, would be like another octave, then I would go to 800, so I'd multiply that one by 2. If I go up another octave, that's going to be 1600 hertz, etc. So you can imagine that if I went up one more octave, I would get up to 3200 hertz. And so you can see that there's 1, 2, 3, 4, 5 octaves to go from 200 hertz up to 3200 hertz. So now you know how to calculate different frequencies. So for example, if I asked you for 30 hertz, and I said, what is the frequency that is 2 octaves up? What frequency? There you just multiply by 2 twice. So it's multiplying by 4, you get 120 hertz is the frequency that's 2 octaves up. Okay, so hopefully that's making some sense to you. Now we're going to move on and talk about waves. Oops, I just realized that I made a mistake here. I thought that the camera was on the whole time when it was not. So let me just review that then. The going up 1 octave takes you up to 880 hertz. So that means the frequency multiplying by a factor of 2. And if I started with 200 hertz, each time that I go up an octave, I'm multiplying by 2. So you can actually see here, going up an octave, going up another octave, going up another octave. So in other words, from 200 up to 3200 hertz is 1 octave, 2 octaves, 3 octaves, 4 octaves. So 1, 2, 3, 4. So I made a mistake. There's 4 octaves. In other words, that there's 5 different frequencies, but that if you wanted to go up 4 octaves, 1, 2, 3, 4, from 200 hertz, you get to 3200 hertz. If I started at 30 hertz and I wanted to go 2 octaves up, I should multiply by 2 twice, and I should get up to 120 hertz. The first octave would be 60, the next one would be 120. Okay, so now we can move on, talking about the wavelength. So let's see here. Okay, so we want to basically review some things about velocity, frequency, amplitude, and wavelength. So this is just kind of a assessment here to remind you. You probably know how to figure out what the frequency is, and now I think you're catching on how to figure out what the wavelength is. Amplitude, I think you got that. And then the wave speed, that might be the trickiest part, okay? And so if I remember correctly, the end of these slides here has the solutions. That is, great. Yes, it is correct. It's close to the end. So I would like for you to try figuring out whatever you can, and then toward the end here we'll discuss how you figure those things out. These are the other parts of the assessment here, and these will be similar to types of things that you'll see on the exams. Okay, so here's some of the physics terms. These are the things that you need to know. What an oscillation is, a wave, wavelength, frequency, amplitude, the difference between a transverse and longitudinal wave, and then polarization. I'll just mention it, but I don't think that this is an extremely critical thing, because this has to do with transverse waves. So everything except this last one is, I think, important. Here's our equation. This is the big one, right? V is equal to F times lambda. This is an important one, and you need to have this one on your crib sheet. You need to know how to work this equation. Wave velocity is frequency multiplied by a wavelength. So here's the deal. If you dropped a pebble in a pond, and the pebble breaks the surface, the water oscillates up and down. That's harmonic motion. The ripples form and start spreading out, and this type of oscillation is called a wave. So if we had a wave oscillating up and down over time in a given space, then we could see that this a ball is going up and down. You could also see it at the instant in time. If we had a bunch of balls, you could see that some were higher and some were lower, right? So this is like a snapshot, and this would be like looking at one ball and seeing what its motion is, right? And so we actually will sometimes graph things as a function of space and sometimes as a function of time. So there's a simulation here, and I will open it up and also give you a link. This is our simulation here, and we can play this here, and the part of the game of this thing here is to be changing the wavelength. There's a little bit of a janky interface, but I think you can get used to it. If I change the wavelength, so let's say I change it to 100 or so, you can see that this wavelength is getting longer, so I'm obviously too long. Let's say if I make it shorter, it seems like it's getting closer, but it's not quite there. And if I make it maybe, let's say 30, it's a little bit too short, so you can kind of play with this here. I wish there was a way to sort of just go up and down, but you can't, because it's kind of old school. But we can basically, I'm getting closer and closer here, and you can play with this until you kind of get to the right wave. So you can see that my red wave is slipping behind here, and if I go shorter, looks like it's slipping faster. And so if I go maybe a little bit longer, so 48, 49, let's try 52, getting closer. So you can play with this here. Oops. So I guess instead of you watching me fumble around to find this, you're seeing that I'm getting very close here. So maybe 38 or something like this. And then now I could try changing the amplitude a little bit, so 36. Yeah, so okay, so the idea here is that you're watching this this ball go up and down, and so you could either look at it as how often is this ball going up and down. It's kind of this basically you can do frame by frame here. In fact, maybe that's the way we should solve this problem here, is maybe instead of guessing. So let's do that. That's going to be way better. Okay, so let me go back to the beginning here. At 0, it's sitting there at the top. Okay, it goes down and then back up. So I said top. Let me rephrase that here. At the beginning, go back. Oh, that's weird. Back means forwards. There's obviously something not quite right with this. Maybe play. That's kind of weird. Okay, there must have been a bug in this thing here. So let me go do like this. Okay, so whenever it's at the top here, it's 5.15. Okay, and now it goes back up to the top again. So 5.9. Okay, so we're going to solve this mystery together here. Okay, so so basically, like if I looked at the ball in time, it looks like it goes down and then it goes back up, and in time, it looked like it took this thing between 5.15 up to 5.9. So the difference is the period is going to be, what is that? 5.7. I'm sorry, it's going to be 0.75, right? So we got because if I added 75 to 15, I get 90. Yeah, so that works. Okay, good. The next thing that I'm going to do is try to figure out the wavelength. So the length of this wave here looks like it's 1, 2, 3, 4, and then plus a little bit. So probably the wavelength is like something close to like 42 or something like that. And actually, without it moving, it is a lot easier to try to figure that out if that's right or not. So maybe 41. That looks pretty good. And the frequency here is going to be 1 over 0.75. So again, if I just go to my calculator here and I do 1 divided by 0.75, oops, I made a mistake. Then we get 1.333. Okay, good. So I'm going to do 1.333, and then now let's see if it works. Looks pretty good. I'm pretty close. I got a 90% score. So I got a B+. So it wasn't perfect. Now if I modify this, maybe I do 0.34 or something like this. 91. That's pretty good. Let me try 1.35 maybe. So it's pretty good, but you see that it is still slipping a little bit. But anyway, we're most of the way there. Okay, so that's what I wanted to show you. And this investigation matching these things can help you to realize the relationship between frequency and wavelength, and looking at the different characteristics of the waves. So the other thing I want you to notice is that in that simulation there, if I made either the frequency or the wavelength larger, it actually travels faster, and you can actually see that by trying this out. Okay, so you can adjust these things to try and match and see how it works. I know it was a little frustrating. You can see it was for me too. So just try it out if it's helpful, and if it's not, then it's okay too. We will have some other examples of looking at these kinds of things. So we'll try to match these here, which we did. But the most important part is that I want you to see, how does changing the amplitude change the wave? How does changing the wavelength affect it? And how does changing the frequency affect it? And so you can actually start to see what are those differences. Draw a graph, showing the amplitude and wavelength of the wave. So you can figure these kinds of things out. That's a snapshot. And then finally, the speed of the wave. If you remember, we have this equation now, speed of the wave is equal to frequency times wavelength. You can actually now begin to see that if you have the frequency and the wavelength, you can calculate the speed of the wave, how fast it moves across the screen. Okay, so this is one of our activities here about transverse and longitudinal waves. And so as you saw with the slinky, that as you shake it back and forth, or up and down, let's say, or you crunch it back and forth, you can see the different types of waves that you're creating. So you're going to be describing what are those types of differences between those waves, and how would you describe it? This is the process of doing physics, is learning how to describe things, and both qualitatively and quantitatively. As mentioned, the amplitude of a wave, and I know this is a bit of a review, but I think it's always good that we go back and check some things again here, that the amplitude of a wave is, you take the center part and you go up to the top, and that's your amplitude of your wave. So remember that in a water wave, the amplitude is going to be measured in distance, maybe in meters or maybe in centimeters, whereas a sound wave is going to be an amplitude difference in pascals, which is a pressure. The length of the wave is, if I took a snapshot of any wave, it would be the distance over which the wave repeats itself. So how many wavelengths appear in this figure? Well, I can see one peak to the next peak, and then one peak to the next peak. So it looks like there's two wavelengths appearing in this figure. The frequency is a measure of how quickly something oscillates. So if all of these things are moving at the same speed here, you could imagine that as this left-hand wave is moving by, that if I was a rubber ducky, I would go up and down slower than, for example, if this right-hand side wave moved by, then I would go up and down very quickly. And so basically the idea is that the faster the oscillations, you can actually see that it has a shorter wavelength or length of the wave. So again, as a reminder, the unit of frequency is hertz, and 1 hertz is a cycle per second. So when a wave has a frequency of 10 hertz or 10 cycles per second, that means that 10 waves travel past a given point at each second. So what would be the frequency of the wave shown below? So you drop a ball. After 1 second, there's 2 waves that have gone by. After 2 seconds, there's 4 waves. And after 3 seconds, there's 1, 2, 3, 4, 5, 6. So that must mean that it looks like there's 2 waves happening every second. So if there's 2 waves created every second, that must mean that the frequency is in fact 2 hertz. So that, hopefully you caught that there, that if I was sitting right here, I would expect, and these made 2 more go by and one more, and after 1 more second, then I can expect that every second I'm going to have 2 waves going by, or in other words, I'll go through 2 oscillations. If I was a little rubber ducky right here, I would go through 2 oscillations up, down, per second. So the frequency of a wave, it conveys information. Frequency of a light wave is actually its color, but the frequency of a sound wave is determining its pitch. So the frequency is remaining the same even if the wave amplitude decreases as it spreads out. So you saw in a simulation before that the amplitude was decreasing as the wave spread out, but the frequency will still remain the same. So the speed of a wave depends on the type of wave and on the medium. And so the typical speed of a water wave is somewhere around 5 meters per second or 10 miles per hour. And the speed of sound in air is around 344 or 343 meters per second, which is about 700 miles per hour. And the speed of light is around 300 million meters per second, or that's 600 million miles per hour. So very, very fast, right, compared with the speed of sound in air. And so this little kind of animation, I guess you could see, is that the darker blue line here is the same in all these different cases. But one of the things that you can notice here is that you can see that as the wave is moving, that's the shaded region, you can see that by the time it completes one cycle, then that shaded blue region has linked up again to the location where this complete cycle, where how do you say, they match up again, I guess is maybe a way of saying it. So I want to try to maybe help visualize that with you here, is that this equation that we have for lambda and wavelength and so on, is that if this wave is traveling with a certain speed, right, then this is going to be just a little derivation or maybe a way to convince you of this formula that we have. Then we could see that after one period, that means after the time t, this part here has moved along until so it moves along like this and moves along more until finally it links up and it matches. And the picture that I have in mind is this one here, that the amount of time that it takes for this shaded region to move over here to get to complete one cycle is one period. And so, in other words, it takes this amount of time. So, how do you say? It takes one period, t, for the wave to travel one wavelength. So, in other words, for it to travel this distance, this wavelength here. And so, actually, what I can say is, remember that thing we said about distance is equal to speed times time? We can use that here. The distance traveled is the wavelength. The speed is multiplied then by the period. That's the actual time that it takes for this wave to move over by one full wavelength. So if you remember that frequency is just 1 over the period, right, then you can actually say that this is equal to v times 1 over f. So in other words, f, if I multiply both sides by f here, f times lambda is equal to v. So anyways, that was just my little sort of simple derivation here, is that this wave is kind of moving, and then moving more, and then moving more, and by the time that it finally gets to match up, that it has traveled one wavelength, and that took place during the time capital T. So that's kind of how we're getting there, and I hope that makes sense to you. And if you want to talk about it some more, try to scratch your heads about it, I'm definitely very happy to discuss that in more detail. But anyway, let's continue to move on here. As a wave moves forward, it advances one wavelength with each complete cycle. So the distance that it travels is lambda. So this is kind of another way of thinking about it here, is that the distance divided by the time, well, that is the speed. So it travels a distance lambda, one wavelength, in the time t, which is the period. And since the frequency is 1 over the period, we can now plug in for this 1 over t as f. So lambda times f is the speed, and that's what we have here. So hopefully I've kind of helped to convince you. There's another interactive equation, which I believe we can, I need to update the link on this thing here, but you can play with this calculator here, or you can actually just do it on a calculator. And if you plug in either the frequency or the wavelength, you can figure out the speed of the wave. Let me know if this simulation is helpful, and I'll incorporate it a little bit more if it is helpful. I don't know if this is going to be a really helpful thing for you, because if you know how to do these calculations and you can plug in the numbers, then I think you're going to be set to solve these kinds of problems. So, for example, if a water wave has a speed of 5 meters per second and the wavelength is 2 meters, well, what is the frequency of the wave? And what we mean by what's the frequency of the wave is, if you're a rubber ducky sitting at one place, how many waves per how many waves per second do you see coming by? In other words, how many times per second do you go up, down, up, down, up, down? So in order to engage with this concept here, I'm going to switch back to the camera view because I'm a little bit of an analog kind of person. And I will write down the numbers and then switch to the camera view. The speed is 5 meters per second. The length of the wave is 2 meters. And we need to figure out what is the frequency. And okay, so we're going to go here to this thing. So here I have drawing my picture here, and here's my little rubber ducky here. Okay, that's my little rubber ducky, and this wave is moving. My rubber ducky staying still and just going up, down, and up and down. But this wave here is moving at 5 meters per second, and the length of the wave here is going to be 2 meters. Good. So I can guess that if it's going 5 meters per second, then I think that within 1 second, this thing is going to go through at least two full wavelengths. So we can figure that out by saying that if I use my formula that F is equal to V divided by lambda, then I can see here that that I can plug in for 5 and plug in for 2. And if I plug in for 5 meters per second and plug in 2 meters, then I'll get 2.5, and you see that the meters cancels out, and I'll be left with 1 over seconds, or in other words, 2.5 hertz, which indeed relates to our intuition that we had about this is a quickly moving wave. This rubber ducky is going to go up and down 2.5 times per second.